So let's go to y equals.
We're winning.
Let's go to y equals. Oh, I should have not delete. It was just a function, right? Say it again.
So we've got a leg up on machines. We're winning.
Absolutely. Thank you for saying that. It's cute. Nope. We will not be able to. So I'm going to use a standard viewing window, although I know that it doesn't, I shouldn't even think of the standard viewing window. I have the graph, so let's adjust it so we can see a better graph. What did I do? Did I copy it correctly? I did. Okay. So the window, I don't need to see anything more than -4, 4 with a scale of 1. Minimum, it doesn't go below 2, -2, so -4, 4 is good enough with a scale of 1. So it's coming from infinity, crossing at -1.29. So this is what I was saying from pre-calculus, when the solution appears 3 times, that is a cross, but a very slow cross. We didn't know more to say about that in pre-calculus. So no one can figure out where the inflection point is. We did. I mean, from the graph you can't say, or you can tell where the inflection points are. Other than this one, you can tell this is opening downward and this is opening upward. Obviously, this is an inflection point. So obviously, this is an inflection point, opening downward, opening upward. But no one can identify this from the graph, and no one can identify this from the graph. So this is the function f of x. -3 x to the 5th plus 5 x to the 3rd. A problem this long cannot be on any test or final exam. It's very clear. You don't have to worry about that. I'll make sure that the problem doesn't require more than 5 to 7 minutes. But this is the concept. This is what we learn about a function from the first derivative, increasing, decreasing intervals, and max min, if any, and what we learn from the second derivative, concavity, and inflection points, opening upward, downward, and inflection points. So first derivative, increasing, decreasing, max min. Second derivative, opening upward, downward, and inflection points. So in summary, in just one sentence, this is what we learn from the first and the second derivative. So I don't want to move to the next section, although 4.4 is done. But we still have to work on 4.4 and L'Hopital's rule and other indeterminate forms. And the 4.5 is exactly what we just did. But I would like to practice, and I would like you to choose, or maybe I should choose a rational function this time, which will be much shorter than what we just did. But is the idea clear? Do you understand how important organizing all the information is in order to be able to graph? Because I have everything here. It tells me everything, increasing, decreasing. It tells me where the inflection points are. It tells me how it's opening up or down, and where max min are. Any questions? This was a lot of work. Also a lot of numbers to determine. Okay. So let's look at, let's say, x squared minus 4, problem 46 on the same page, 299. F of x equals x squared minus 4 divided by x squared plus 4. Now remember, rational functions have problems. Polynomial functions did not, meaning what could go wrong with a rational function?
The denominator being 0.
Exactly, asymptotes. Yes, asymptotes. That is the problem. Vertical, horizontal, or slant. Good. So the first thing I will do, I will just factor the top. I cannot factor the denominator. That's not factorable. And luckily, the denominator is or is never 0. Is never 0 because x squared plus 4. So this function is nice. It's rational, but it's defined everywhere. Okay. So let's start the table. F prime, f of x, and the second derivative. All real numbers, so at least there are no vertical asymptotes. The function is defined everywhere. Okay. Let's study the function first, and then go to the first derivative and the second derivative. Okay. So what can you say about this function? What can you say other than the fact that it has no vertical asymptotes and it's defined everywhere? It's a rational. It's a rational function. That's okay. So now when is x 0? When is x 0? How much is y? Perfect. Where are the x-intercepts of this function? So we plugged in 0 to get -1. Where are the x-intercepts of this function? When x is 2 or -2. Is that clear? When the numerator is 0? Is that clear, everyone? Yes? Okay. And of course, limit from x squared minus 4 over x squared plus 4 as x approaches infinity or negative infinity. It's not going to make any difference. What is this preliminary situation? I need to know what situation this is. Nice, I like that. Because it's a ratio, and because it's infinity over infinity. L'Hopital, very good. So limit as x approaches infinity from good over. Very good. These two go away. So what is the limit? Of course, we know that from pre-calc. As long as the top and the bottom have the same degree, it's the leading coefficient over the leading coefficient. I make myself a note. Y equals 1 horizontal asymptote. There is nothing else we can find about the function from the function itself. We exhausted everything. X and y intercepts, and behavior, asymptotes, this horizontal asymptote, and there is nothing else. Now we can proceed with the first derivative. F prime of x, the numerator prime is 2x times the denominator plus, I'm sorry, I meant to write minus, x squared minus 4 multiplied by 2x divided by, I was just getting ready to say that some of you forgot to differentiate the inner function on the test. So 2x times the denominator minus the numerator times the denominator prime over this. I will definitely factor out 2x. Always factor out as much as you can because you will make everything easier to work with. So then we have x squared plus 4 minus x squared plus 4. These two go away. 4 plus 4 is 8. So this is 16x divided by x squared plus 4 squared. Okay, that's all I needed. Is there a critical number? Can f prime be 0? When x is 0. Very good. This is the only critical number. So we go back to the table. I write 0 under 0. This is the only critical number for this function. And I have to study, I don't have to, but I prefer studying the sign of the first derivative now. What is the sign of this no matter what? Because I don't want to waste my time. Always positive. So I'm only going to look at x. So before 0, what is the sign of the first derivative? So this is all positive, but I do have an x in there. Negative indeed. And after 0? Very good. It wasn't that difficult to find the sign of the first derivative. I would not personally wait till I determine the second derivative. Now, this is the moment of truth. If these two do not work well together, I say, oops, I have an error somewhere. Let's try. From 1 to 0, what does the function do? Decrease. Is that supported by the sign of the first derivative? Good. It decreases. From 0 to -1. Good. I write them small because who knows, I may have to come up with some inflection point in there. And I have to erase it because I won't be able to see. So between -1 and 0, is that supported by, okay, increase. And from 0 to 1, okay, it appears that there is no error, at least so far. Now, I really, really don't want to determine the second derivative because it's a lot of work, but I may have no choice. There may be an inflection point in there. So I have to go and do it. Okay? So I'm going to differentiate. So this is f prime one more time. 16, leave 16 outside. There's no point in carrying it anywhere. So I'm only going to differentiate this. And 16 can stay outside and wait. So then the second derivative equals 16 divided by x squared plus 4 to the 4th power. Okay, this is a little bit messy. The top prime is 1 times the denominator. X squared plus 4, everything squared, minus the top multiplied by the denominator prime. 2 times x squared plus 4 times 2x. I have no choice because there may be an inflection point. Maybe not. Maybe all this work is in vain, but I have to try. Please remember factoring. It's absolutely crucial to factor out x squared plus 4 to the 1st power. So 16 x squared plus 4. One thing that I wanted to mention about the second test is sometimes you write things but you don't put parentheses. Without parentheses, you're changing the problem, so be careful. I put some parentheses here and there. I did not deduct points for that, but please remember, if I write this without parentheses, I'm adding or subtracting, I'm not multiplying. So be very careful. So this is x squared plus 4 to the 4th power. Now there is one left here, x squared plus 4. This will be gone because it's outside, minus 4x squared. Yes, I will get rid of one of these. That was one of my target and hope. Although that's not a big deal, it's not a problem, it's never going to be 0. So then 16, and then this inside is negative 3x squared plus 4 over x squared plus 4 to the 3rd. So actually the function has 2 inflection points. So when I said this equal to 0, but first I would like to factor out -1. So I have 3x squared minus 4. So all this work was not in vain. Was not wasted. When I set the second derivative equal to 0, I will have to write 3x squared minus 4 equals 0. One more remark before we continue. If you do not leave the coefficient outside, you will really make it difficult. So please leave the coefficient outside. It's not going, if it's a factor, it's not going to affect the answer, and it will be always easier than carrying this 16 inside at the numerator, in the numerator. So then I move forward, divide by 3, so I get x squared equals 4/3. I take the square root, x equals plus or minus the square root of 4/3. I put in the calculator to see what this is, so I can put it back. So the square root of 4 divided by 3, and I got 1.2, roughly. So approximately plus or minus 1.2. Okay, I go back to the table. Negative 1.2 and positive 1.2. Negative 1.2, 0, 1.2, 0. I will have to find the value of the function at these points and also study the sign of the second derivative. Okay, let's plug in a number. So here's the second derivative. This quantity, always identify the quantity that you don't need to work with. What is the sign of this quantity no matter what? Correct? Always positive, because it's x squared plus 4, which is always positive no matter what, and 16. So I only need to take care of this. So let's say it's easy to plug in 0. When I plug in 0, I have negative with negative 4, so this must be positive. Now let's see outside. Let's say I plug in negative 10. Negative 10, this will be positive with negative 10, or positive 10. This will be positive, and this will change the sign. So it's opening downward, opening upward, opening downward. Once I have this number and this number, what will negative 1.2 comma this be, knowing that the second derivative is 0 and it changes sign? What will this point become? Negative 1/2 comma, I didn't determine that yet. Inflection point. What will this become? Negative 1 or 1.2 comma this, which in a moment I will find it. Inflection point. Also, I forgot to ask you, what type of point is 0 comma negative 1? When I know the first derivative is 0 and it changes sign in this way. Very good. Local minimum. Thank you. Okay. That's the last thing, and of course the function is even. If we replace x by negative x, nothing will happen. So what I have in the first quadrant is going to be a copy in the second. But let's determine these two. So when I plug in the function, negative 1.2 or 1.2 is the same thing. So 1.2 squared minus 4, and I divide by 1.2 squared plus 4. Okay, I got negative point. Is it negative? Yes, it is negative, because the top will be negative, yes. So I got negative, roughly, I'm going to write negative 0.5. It's not negative 0.5, it's a little bit less. Okay, ready? Okay, that's all I need to graph this function, just this table, nothing else. When we graph a function with asymptotes, what do we have to graph first? When we graph a function with asymptotes, we have to graph the asymptotes first. So there is only one asymptote for this function, and it's y equals 1. Okay. Ready? From approaching 1, opening downward and decreasing, it's going to negative 2, 0. From approaching 1 gets to negative 2, 0, opening downward. It continues to decrease, still opening downward, to negative 1.2, comma negative 0.5. So continues to decrease. still opening downward till this point. Then at 0, -1, so it continues, it changes concavity, opening upward, and it goes to 0, -1. I don't have to look at the table anymore because I know the function is even, and I only have to copy everything on the other side. This is the graph of f of x equals x squared minus 4 divided by x squared plus 4. You can go back and put in the graphing calculator. Do not forget, if you try to check with a rational function, you must put parentheses around the top, mandatory, x squared minus 4 divided by x squared plus 4. The graphing calculator will not add the horizontal asymptote. We have to add it in. Let's say I'm happy with the same viewing window for now. And graph. Here it comes. And now the horizontal asymptote. The inflection point is somewhere here. But it's very hard to tell. And here. At, what was it? 1.2, where is my table? 1.2, comma, -0.5. Any questions? What I recommend, in order to consider this clear, let me make one up and you will work on it. Is that okay? On your own? You prefer a rational? You prefer a polynomial? Okay, I'm going to try to find hopefully an easy one like 33 on page 299. There are many other types of problems that we're going to look at, but let's look at x cubed minus 12x plus 2. We want to determine everything. By everything we mean limits, x-intercepts, y-intercept, first derivative, max min, increasing, decreasing, inflection points, concavity, second derivative, and the graph. If you allow me to draw your attention to the graphs that they are presented in the book just for 1 second. I'm not saying this is a method that doesn't work. I'm only saying there is no summary. It just goes through A, B, C, D, E, F, G, but there is no summary, and all of a sudden they come up with a graph. Same thing in example 5. Some stuff, and then they come up with a graph. There is no summary. It only says f prime is greater than 0 when x is between -2 and 0, and f prime is less than 0 when x is between 0 and 2. I accept the method, but I truly believe that it's very difficult to put it together. So use a table. If you don't like the one we are using together, create one on your own, such that it'll help you put everything together so you can graph it. Raise your hand and let me know if you need help, and I'll come and help. Anyone needs help with this? Now, what is difficult here is to find the x-intercepts. So this is degree 3. It can cross the x-axis once or 3 times. So you can do this, right? Because it's a positive leading coefficient, it's going to look like this. It can cross 3 times or only once. So that needs to be determined with the graphing calculator. I don't know why they stopped producing TI-86. This is my favorite calculator, and I'll show you why, especially for polynomials. So TI-86 has a feature called poly. See, poly. And when I click on poly, it says order, which means degree. I put in degree 3. It's asking me to put the coefficients. The coefficients are 1, 0, -12, and 2. And all I have to do is click this button and say solve, and it gives me the solutions, real or not. There are 3 real solutions. You can copy them now if you'd like. 0.17, 3.4, and -3.5. This is so easy to determine with TI-86. Is it difficult with 84? No, but you have to find them with graphing the function and then finding the zeros. So one is x equals -3.5, the other one is 3.4, and the other one is 0.2, let's say. So you have the x-intercepts. The rest should not be, hopefully, not too difficult. So when you start creating the table, assuming you like this order, it's a polynomial, so it's defined everywhere. You should put these 3 values in the table, and 0 as well. So 0.2, and this is 0, 3.4, and this is 0, and -3.5, and this is 0. Can anyone give us the limits at infinity and negative infinity? As x approaches negative infinity, this is the most powerful. Where will it go? Do you all agree? And then the other one is positive infinity, which we knew. We knew this from pre-calculus. This is degree 3. And then you have to find the y-intercept, which is not difficult. So that is 2. There's nothing else you can find about the function from the function itself. Now you have to go to the first derivative. I don't know why they discontinued these calculators. I have no idea. Why don't they? Why can't they put this feature in the other calculator?
I'm sure you can probably download it somewhere.
Yeah,
That's
very
maybe
possible.
right now.
Yeah, this is my favorite calculator. So were we able to, that's 7, it's 8. Were we able to determine the critical numbers easy? Oh, yeah, not too bad, not too bad. So f prime of x equals 0 means x squared equals 4, or x equals plus or minus 2, correct? Okay, that was not too difficult. So careful where you put them in the table. Sometimes it gets crowded. Like, I think it's going to get crowded. Let's study the sign of this, which is not difficult. Let's plug in 0, so it's negative in between. And if we plug in any other number outside, it's going to be positive. So far, other than finding the x-intercepts, so far it's okay. So now I would like to not wait till the second derivative and see if these two work well together. So from negative infinity to 0, is that supported by the first derivative? Yes, it is. From, I have to determine this point and this point, the y value. So I have to plug in negative 2, so this is negative 8, right? Plus 24 and plus 2. I got 18, correct me if I'm wrong. And when I plug in 2, I get 8 minus 24 and plus 2. So this is negative 14. Am I correct? Did you get 18 and negative 14? Okay. So from 0 to 18, what does the function do? So is it okay? Good. So far it's okay. From 18 to 2. Okay, and that's okay because the first derivative is negative. From 2 to 0. Yes. From 0 to negative 14. Good. And then from negative 14 to 0. Good. And from 0 to infinity. It appears that everything is all right. I only have the second derivative now, which luckily is 6x. And 6x is 0 when x is 0. And the sign of 6x before it's 0 and positive. What type of point is 0, 2 when I see that the second derivative is 0 and it changes sign? Zero, 2, the second derivative is 0 and it changes sign. Inflection point, thank you. What type of point is negative 2, 18? The derivative is 0 and it changes sign. Max, local max. And what type of point is 2, negative 14 when the first derivative is 0 and it changes sign from negative to positive? Local min. This is it. There's nothing else. Let's graph the function. It goes high to 18, low to negative 14. I have to plan on that. So negative 3.50, negative 2, I'm going to say 2, well maybe 4. 4, 8, 12, 16, 20. So I'm going to say at negative 2 is 18. Then at 0 is 2. At point 2 is 0. At 2 is negative 14. 4, 4, 4, 4. And 1, 2, 3.4. Okay, let's see if I put all the points. Negative 3, yes. Negative 2, yes. 0, 2, yes. 0.20, yes. And 2, negative 14, correct. Okay, ready to graph this? Coming from negative infinity, increasing, crossing the x-axis and increasing to this local max. Opening downward all this time. Then it continues to open down and it's coming to 0, 2, which is an inflection point. It changes concavity, starting opening up, and it crosses the x-axis and goes to this minimum at 2, negative 14, opening upward, and it gets to 2, negative 14 as the local minimum. It crosses at 3.4 and goes to infinity. So this is the function f of x equals x cubed minus 12x plus 2. Any questions?